All right, so good afternoon, everyone. We're really happy to have Professor Tsai with us. Thanks to the support from IAS, the School of Business, and the Department of ISOM, we are privileged to have Professor Tsai as a regular visit. And Professor Tsai is one of the most influential statisticians of our generation, and he is the 2008 Corps President Award winner. In addition to his impact for research, Professor Tsai played leading roles in our society. He has been the editor of the Annals of Statistics, the president of the ICSA, and in August he will be the president of IMS. All right, so we are really happy to be able to have Professor Tsai with us. All right, so Tony, the floor is yours.
Yeah, thank you, Xinhua, for the kind introduction, and it's always happy to be here. And I already gave a talk on transfer learning about 2 weeks ago, and today I'm going to continue the discussion on what's called multi-source learning. And today's focus is on federated learning, which is a very popular topic currently, especially in machine learning. But before that, I want to make some general comments about a very active discussion or debate right now in the age of big data and the AI about the relationship between statistics, data science, machine learning, and AI. If you pay attention, there are lots of discussions right now about which role statistics should be playing in the new age of AI. And I want to give you some encouragement. We have a very good friend in Tom Sargent, who is a Nobel Prize winner in economics in 2011. And I quote him that he said, AI is actually statistics. So AI is statistics. It's not like statistics is very important to AI, which most people agree. But if we talk to our computer science friends, probably they disagree that AI is statistics. But according to him, that AI is actually statistics. It uses very gorgeous rhetoric. All AI uses statistics to solve problems. So we should be very happy that we are born in such a very interesting moment in history. But if you think about statistics or machine learning or AI, whichever term you use, and the whole field is mainly driven by application. And there's a wide range of applications in many, many different fields. And because essentially all experimental science generates data. And once you have data, what's left is data analysis, and that's us. And people develop methods, and lots of methods. And some we know it's based on some very principled thinking. And some we actually don't know why it works. So our field is very different from hard science. Think about, say, rocket science. You don't shoot a few rockets first and try to see which one works. You have to understand the principles of physics very well before you try anything new. But in data analysis, it's very different. For example, deep learning. It's very successful for a range of applications. But we don't actually know why it works. We are very far from understanding deep learning. So in terms of development, theory is very small. And also discussion about the relevance of theory to applications. There are people who feel that theoretical statistics is becoming more and more irrelevant. But to me, the theoretical statistics is becoming more and more relevant because there are so many methods, we have no idea why it works. Or if we encounter a new problem in the future, what kind of methods are feasible, or what kind of method should be tried first. But anyway, so today I'm going to talk about federated learning. So I'm going to review a few slides. I remember I gave a talk here last year. So maybe if you were here last year, you may have seen the next few slides. In statistics, we try very hard to understand optimality. And this optimality is understood with respect to the sample sizes and statistical model. Basically, giving a sample from a class of models, we want to know what's the best way to come up with an estimation method or a test or a confidence interval. So we tried very hard for last almost 80 years under a range of criteria like admissibility, efficiency, minimacity, and so on. We basically try to understand, giving the data into the model, what's the best way to do it, no matter which problem you're interested. So I'm going to use minimacity as an example to discuss this further. So whatever you observe, let's call it X. This X comes from some model called P, or some distribution. And this distribution belongs to a certain class of distributions. And given this X, we want to estimate or understand certain aspect of this distribution. So theta of P is a parameter. It can be the mean of the distribution. It can be the density function. It can be anything of interest, regression coefficients, anything. And what we do is we first try to come up with, based on X, we first try to come up with an estimate called theta hat. And then we want to evaluate the performance of the theta hat by the maximum error. So it's soup over all possible values or class of distributions. What's the maximum error? So as an analogy, you think of, say, suppose you have just bought an expensive watch. So you want to keep track of time. So the question is, how good is the watch? Certainly some people value by its price. If it's expensive, it must be good. But typically, as a watch, we want the watch time, the difference between the watch time and the actual time to be small. So what we do is we look at the maximum error, say, over a cycle of 24 hours. And that maximum value quantifies the accuracy of the watch. So if we have an estimate theta hat, this maximum risk also quantifies the performance of the theta hat. If we all agree on this maximum error, then as an analogy, what's the best watch? The best watch is the one that minimizes the maximum error. So that's a minimax. That's a minimax estimate. The minimax estimate is a procedure that minimizes the maximum error. And people have spent a lot of effort trying to come up with minimax estimates for a range of problems, from very simple problem like normal mean problem to much more complex models. If you count the number of papers, there must be tens of thousands of papers on minimax procedures. So what I call this as classical minimacity. And this notion has been around for at least 70 years. But lately, I think there are a range of problems that's similar but different, what I called post-classical minimacity. So as a statistician, we still observe some data, and this we still called X. So whatever you observe is called X. It comes from some distribution, and we still want to understand the distribution, some theta of P. And what's different from before is that we are no longer interested in all possible estimates or all possible procedures. So again, as an analogy, say watch. And we know that some watch are very expensive. Let's say gold watch. And you only buy gold watch. And the less expensive ones are of no interest to you. So then your question is, what's the best gold watch? So we constrain ourselves to a subclass of watches. So here it's to a subclass of procedures. And then, of course, the first question is how to construct an estimate that satisfies the constraint. And then giving the estimate satisfies the constraint, and you also want to evaluate its performance by the maximum error. So same thing. Once it's a gold watch, you still measure the accuracy by the maximum difference between the watch time and the actual time. And then, of course, within this constraint, we want to construct the best possible watch of this type. So we want to construct the constrained minimax estimate. So within this subclass of estimates, which one is the best? And then the corresponding quantity is a constrained minimax risk. Now the question is why we constrain ourselves to a subclass of methods. And not only that, actually this constraint is non-statistical. That's something new. If you follow the discussion or debate between, say, what's the difference between statistics and data science, I think this type of problem that involves non-statistical constraints belongs to data science and not to classical statistics. So let me give you some example. The first one is privacy. I don't think I need to give you any justification for the importance of privacy. So we want to do data analysis and as accurately as possible, but we also have obligations to either your clients or your patients. You have to preserve their privacy. And in some problems, the constraint is the distributive nature of the data. In all classical statistics, no matter which specific problem you want to solve, you always assume there's a single data set, the one pile of data set somewhere waiting to be analyzed. But now there are more and more problems where data is distributed. It's not in this one single place. It cannot be either by its size or it cannot be because of security or privacy. And there are also considerations of computing. Especially for online learning problem, you want to make a decision as fast as possible. So whatever method you use, it has to be computed very fast. And once you have computational constraint, then again, you are no longer interested in an estimate that takes a long time to compute. And there are some interesting phenomena I mentioned in my previous talks, that there are certain statistical problems. It turns out if an estimate is accurate, if it's statistically good, it has to be computationally infeasible. So in other words, if it's good, it must take a long time to compute. But you don't have the time to wait. So the question is, can we do something very quick, but still have certain, say, accuracy? And there can also be other considerations like fairness. And a lot of discussion right now about whether machine learning algorithms are fair. It turns out it's not. Machine learning algorithms can be very biased. Actually, all these recommendation systems, I think it makes our society more pulled to extreme. You only read news that you like to read. And your worldview actually is changed in the process because you think that's the world. And before, at least we read newspapers. and there are different newspapers with different point of views. Now the recommendation system only sends you the news that you like, and it reinforces itself. So there are lots of statistical problems of this type, where we still want to achieve statistical accuracy. But we have a lot of other constraints, whether it's privacy, communication, computation, and so on. And one particular kind of problem is today's topic, is federated learning. And I think this picture summarizes everything. So in federated learning, you can easily imagine a group of people try to solve the same problem together. So in this problem here, think about any disease. Let's say diabetes. Everyone wants to solve, want to cure diabetes or any given cancer. But where are the data? Some of the data could belong to, say, a community hospital. So this hospital has treated many patients, say, with diabetes. They have the data. But other research medical centers, they also have data about diabetes patients. It could also be, say, other treatment centers. So you have a range of organizations. Each one of them have their own data. Now the question is, can they collaborate to analyze data concerning diabetes or any particular cancer? And certainly the best thing to do, no question, the best thing to do is to combine the data together. So you can imagine you as a researcher, you talk to this hospital and you ask them whether you can bring a USB to copy their data to your USB and bring back to your office. And you do the same for each one of those organizations. And the answer is almost universally no, because it concerns privacy of the patients. And you are very lucky if the hospital allow you to access their data and take away an output that guarantees privacy. And so each hospital has its own data. It's private data you cannot take away. You cannot publish the data itself. But you can run your local model and take away an output that preserves privacy. Think about linear regression. Suppose you want to run high-dimensional linear regression or just least square low-dimensional linear regression. So you can run that regression using the data on this hospital. You can take away the regression coefficients, but you have to guarantee the privacy of the patient. And suppose you can do this on each one of those organizations. At the end of the day, you have a global model. You want to estimate the common parameter, in this case, regression coefficients, as accurately as possible at the very end. And the question is, what's the best way to do it? And it turns out the problem is complicated. And this has spurred a lot of research in the last few years on this topic. So if you look at the number of publications on federated learning, you can see the exponential growth. Yeah, it's almost nothing, and then it grows very fast, because there are more and more problems in real life that requires what's called multi-source learning or federated learning. So how can we learn the global model accurately while preserve the privacy of each, say, organization? So here's an illustration of federated learning. So we can think of this problem as follows. So you have data set 1. So this first data set, it contains, say, observations on N1 patients. So you have measurements Z1 through ZN1. They generate from one model. And what's important here is there's a theta here that's common to every model. But it also can contain some other parameter that's different. So they don't have to be IID. And the parameter of common interest is the theta. So in theory, each one of them can analyze their own data and come up with an estimate of theta hat. But typically, the estimate is not very good. The reason is N1 is typically small. So you don't have many observations. So here, each data set can be analyzed, and you can take away something called a transcript, called T1. T1 is something you can output. So you send to the central server. So you analyze the first data set, you generate T1. You analyze the second data set, you generate T2, and so on. So this central server receives T1 through Tm. So you receive M transcripts. And at the end of the day, you want to come up with an estimate theta hat, which is a function of T1 through Tm. And this is so that, as I said, the T's are called transcripts. T1 through Tm are called transcripts. And also this communication scheme is called independent protocol. Independent protocol means that once you analyze the data, you take away T1 with you. You never go back. You don't have communication in the other direction. If you have communication in the other direction, it's called interactive protocol. For the purpose of today's talk, independent protocol is fine. It's optimal. But for some more complicated problems, it turns out that communication protocol matters. Sometimes interactive protocol is strictly better. And if you think about this slightly longer, you realize that there must be some constraint. If there's no constraint, if you're allowed to do whatever you like, then the optimal strategy is to do nothing. You output the original observation to the center. In other words, T1 is simply all the raw data. And then the central server has access to all the original data. Then we're back to the old classical setting. You have one big data set you want to analyze. Then nothing is new. But as I mentioned earlier, there are constraints. For many problems, there are constraints, either communication constraint, computational constraint, or privacy constraint. And today we are going to focus on privacy. So here's the illustration of the problem. So we have the observations. Z1 is the first data set, Z2 is the second data set. And you output a transcript that guarantees privacy, epsilon delta differential privacy. So after receiving all those transcripts, you want to come up with a single estimate theta hat. And our constraint is differential privacy, which I will discuss in more detail. So if you think about this problem, what's the goal? We can think of the goal in two steps. The first goal is, what's the best possible performance under this framework? Because we have constraints. So you can see that here, we are no longer interested in all possible estimates. We are only interested in the estimates that satisfy the distribute epsilon delta differential privacy constraint. And two is how to come up with a procedure, how to come up with a good estimate that achieves this best possible performance. And also, if you think about this a little bit more, you realize that there are some new features that's different. But assuming that we know how to solve the old problem is a single data set. Suppose we know how to analyze a single data set. Then the most naive approach is each one of us, if we go back to the picture, suppose we know how to analyze a single data set. Then the most naive approach is each one of us try our best to come up with a best estimate theta hat that depends on your own data alone. Then send to the center. And the center, after receiving, say, theta 1 hat, theta 2 hat, all the estimates, then the center can easily take an average. So the naive approach is optimal DP estimates plus averaging. If this works, it will save us a lot of effort. But of course, if this works, I wouldn't be talking about this problem today. And this approach almost always suboptimal. It's not good. It turns out that learning something alone is very different from learning collaboratively among a lot of people. Suppose in this room, each one of us has our own data set. And we can certainly analyze our own data set very well using any method you like. But we also know that each one of us are trying to solve the same problem. It turns out if we collaborate, then we shouldn't try too hard for each one of us. So in other words, in the previous picture, T1, T2, T3, individually, they may not be a good estimate. And they shouldn't. If each one of them is a good estimate, turns out the final estimate cannot be good. So in terms of the new features, if you think about federated learning, there are two features that's different. The first one is privacy. So for a single data set, how to do, say, optimal statistical estimation under DP on a single local machine. Two, of course, is the distributed learning. So now the data is not in a single place. They're spread among M servers. And the question is, how can we learn in a distributed fashion? So the problem is divided into two steps. The first step is how to do it, how to achieve privacy if we only have one data set. And the next step is how to extend this to multiple servers. How to achieve privacy turns out to be a very important problem. I think everyone understands in abstract the notion of privacy. And the first attempt is to anonymize. So think about hospital patients. And patient data can roughly be imagined as an Excel spreadsheet. So you have patient name, and then you have, say, maybe hospital ID number, and then all the clinical measurements, blood pressure, temperature, everything. So you have a big a spreadsheet, or you can think of as having a matrix. And we all know that name is identifier. So anonymizing meaning that we remove the first column. So now you don't see the name. But the second column probably is the ID number. And that's still not good. It can identify the patient. So you remove that as well. Suppose starting from the third column on, it's all about clinical data. So the question is, suppose we remove those two columns and only say publish the remaining columns, can that guarantee privacy? If that's okay, then of course it's easy to achieve, but turns out not. And the most famous example is the Netflix example. Back in 2006 to 2008, for 3 years, the American company Netflix sponsored a worldwide competition about movie rating. So there, the goal is very simple. So each row is a customer. So each column is a movie, and customers watch movies. And after watching movies, you give the movie rating. If you like it, 5 star. If you dislike it very much, it's 1 star. So it's 1 through 5. And to the company, they want to know this movie you haven't watched yet, how likely you are going to like the movie. So recommendation system for movie or for any online markets, they always want to know which item you are likely to buy. So they want to know how likely you are going to like this movie. It was very successful. And after 3 years, the winner took away $1 million. And the company wants to do the second time. But before they run the competition the second time, a team of researchers published a paper and basically showing that the anonymized data they publish by the company, together with a public database, they were able to identify the customers without the name or anything. And because of that, the company has to cancel the second competition. And there's no more competition ever since. So only removing the name or ID number is not nearly enough. And then the question is, suppose we don't publish detailed personal data, not at personal level, but publish only aggregate data like summary statistics, sample mean, sample variance, and so on. And can that guarantee privacy? It turns out the answer is still no. And that's much more surprising. So in this well-known paper, Homer et al., they published a paper back in 2008. And it's quite shocking that to show that publishing the sample mean actually does not guarantee privacy. And that's very surprising. And so I give you some intuition in terms of why it's not private. So releasing X bar does not guarantee privacy. So here's one useful and interesting example, quite insightful. So in this example, we have a total of 136 patients. And each patient's gene expression level was measured. So each patient has about 347,000 SNPs. So again, you can think of as a big matrix. The total of 136 rows and 347,000 columns. And we divide the patients into 3 groups. And the first group are those under study. You can think of this, say, study of certain cancer or, say, HIV. And those are the patients under study. And another group of 50 patients are out group, meaning those are the patients without the disease. In addition, we have 36 reference patients. doesn't belong to either group. And then we release or we compute the sample mean. So the sample mean, you can think of a matrix of size 50 rows and 347 columns, 47,000 columns. The sample mean, of course, is the column average. So this is also a vector of length 347,000. And you do the same for the reference group. So all we know are the two mean vectors. We don't know individual patient measurement. And then we ask the question. Suppose we have a patient called Y. This patient Y is either in the in group or in the out group, either one of those two groups. So either the patient has the disease or the patient doesn't have the disease but belongs to this group. And is it possible to determine whether Y is in the study or not in the study? Because if you can tell that, then it's not private, meaning that knowing the sample means will enable us to identify a patient to determine whether this patient is in the study group or not in the study group. And it turns out the answer is yes. And not only the answer is yes, actually it's easy to do. You just calculate something called the Q value. So this Q value is simply the inner product of this Y with the difference of the two sample means, because they're all vectors of 347,000. So you just take the inner product, and you can see that there's a clear separation between the two groups. So the red one are for the patients in the study, and the green one are for the patients not in the study. And you can clearly see the clear separation between the two groups. If you think about this slightly more carefully, you realize that it's not a big surprise. And the reason is quite simple, and also it's consistent with the Folk law. And the Folk law says in the high dimensional space, because each vector is of length 347,000, so the dimension is very high. In the high dimensional space, two random vectors are almost always orthogonal to each other. So in other words, if you have two random vectors, you take an inner product, it should be very close to 0. But if you look at this here, Y is either in the class, in the study, or not in the study. Suppose Y is in the study, what happens? This first term, MAF in, is the sample mean of all those Ys of the 50 patients. If Y is in the study, then this average contains Y in that average of 50 patients, right? So if we write this out, then one of the terms actually is Y itself. So when you take inner product, Y is taking inner product with itself. All the rest are the other patients. Relative to Y, those other patients are like random vectors. So in other words, when you take the inner product, when Y takes inner product with itself, the term is very large. The rest are much smaller. So if Y belongs to the in-study group, this inner product is large. On the other hand, if Y is not in the study, then Y is not part of this average. Y is also not part of that average. Y is different from all the rest. So when you take the inner product relative to Y, it's random. And that's why there's a clear separation between the two groups. And this example shows that even publishing X bar does not guarantee privacy. And that makes the problem much more difficult and also more intriguing. So what should we do? But before we do anything, we first need to define the notion of privacy. That's not easy. At some abstract level, each one of us understands the privacy. Basically, what's privacy? Privacy means I don't want you to know what I have done. That's privacy. But how do we define this mathematically? Actually, it takes some effort. And now there's a widely accepted notion of differential privacy, which I will explain in a moment. But there are also other notions like local privacy and so on. So roughly speaking, DP, differential privacy, is a concept of protecting the information of individuals when releasing statistical analysis results, like that X bar. And DP has been widely used by tech companies and also by US government. I think the most important application of DP is that it's incorporated for the first time in the 2020 US Census. Because US Census only publish data at aggregate level, right? Say median income, population size, and all that. It never publish individual level data. But still, it doesn't guarantee privacy. So that's why they have to do something extra to guarantee privacy. And this is a definition of differential privacy. And it's fairly similar to robustness in statistics. In robustness, basically, when you want to measure the sensitivity of the output or the statistic to the change of, say, one or several observations. So here, it means that we have two data sets. Think of patients. You have one group of patients consists of n individuals. Now suppose we replace any one of those patients by someone else. So that group, this consists of n patients, and this data set consists of another n patients. The only difference between these two data sets is they differ by one patient. The rest are all the same. And what this says is that the value of the statistics, this m of x is the statistic, like sample mean. The value of this statistic does not change much. Because if this value changes significantly, like in the previous example, we see a clear separation. Then we can tell whether someone is in the study or it's not in the study, whether someone is here or someone is not there. And our earlier discussion, I should mention that here we have two parameters. One is called epsilon and one is called delta. So epsilon and delta together, they measure the sensitivity of the privacy parameters. The smaller, the stronger requirement for privacy. And given the main issue is that goal is that given if you know that statistic m, and if it's private, then you cannot differentiate between x and the x prime. So you cannot tell whether this m is computed based on x or based on x prime. If you cannot tell, it means that you cannot identify any single individual patient. An earlier example says anonymized data doesn't do it. It's not enough simply to remove the patient's name. And also X bar, actually any summary statistic is also not private. But how to achieve privacy? It turns out achieving privacy itself is not that difficult at all. All you need to do is to randomize. So in the previous case, we show that mx of equal to x bar does not guarantee privacy. So instead of releasing x bar, what we should do is we should add noise to each coordinate of x bar. So you just add more noise to it. And after adding noise, you can see that if you compute the Q value again, they're all mixed up. If they're all mixed up, then based on the value, certainly you cannot tell whether it belongs to the study group or it's not in the study group. Not only that, you can prove not only Q value does not identify any patient. There's no other method. So in theory, you can show that no matter what you do, you cannot identify any single individual. But once we know how to solve a problem, you realize very quickly there are many more problems. First of all, how much noise is enough? Maybe you have added too much noise. And two is, in this case, it's called a Gaussian mechanism, because here we add Gaussian noise. And we all study statistics. We know there are lots of choices for distributions. Why we add Gaussian noise? Why not say uniform or Laplace noise or any other distribution? So we want to know what's the best way to do it. But before that, at least we have a general result. So for any statistic, and we define what's called L2 sensitivity, which is the L2 norm if we perturb the data set by only 1 point. It turns out if we know this value, delta 2, then we can add to the statistic noise, Gaussian noise at this noise level. And this will guarantee epsilon delta privacy. So at least we have one method guaranteed to achieve privacy. And the question is, what's the best way to do it? Whether this is the best possible way to do it. And there are many experiments, and people tried on the CFA10 data set, and people have also tried on census data set and other data set. Because as statistician, we know adding noise will never increase the accuracy. It can only downgrade the accuracy because we have something called the strong data processing inequality. So adding noise is always make the inference procedure less accurate. Now the question is, suppose we insist on privacy. So we must have privacy. Now, what's the best statistical accuracy that can be achieved? So if we think about this in such a way, we can divide it into 2 steps. The first step is to quantify the cost of privacy in terms of statistical accuracy. Because before, we are allowed to use any method with or without privacy. Then the best possible method has certain performance. Think about watch. Suppose you can say you can do away with gold watch. You don't need gold watch. Any watch is fine, as accurate as possible. Let's say atomic watch, very good. It's very accurate. But now, if you have some constraints, so in this case, we have privacy constraints. Under this constraint, you can no longer use certain types of watch, and then it will be less accurate. So the cost of privacy in terms of statistical accuracy. And then we want to develop the optimal algorithm, develop efficient algorithm that achieves optimal statistical performance with DP guarantees. So under these constraints, what's the best way to do it? So if you remember in the beginning, we have 2 slides. One is a classical minimexity. That's the best performance without any constraint. Then we have the post-classical minimexity with the constraint. So basically, we want to know what's the difference between those two. And in the last few years, I've been working with my collaborators. And Ling Jun was my former PhD student, now on the faculty of Rutgers. And Yi Chen graduated 2 years ago, and he's now at Amazon, and he's writing code every day, implementing private algorithm for Amazon. And Abhinav is my current PhD student, and Lassie is my current postdoc. And they're all very smart. So we have looked at a range of problems and try to quantify the cost of privacy, and also try to develop technical tools that enables us to analyze statistical problems under privacy constraints. And we have also looked at the federated learning setting, and that's the parts that I'm going to discuss next. But before, I want to give you a summary of the analysis that we have been doing over the last few years. So we have looked at a range of statistical problems, and these problems are quite standard in statistical literature without privacy constraint. And the question is, if we want to do the analysis under these models with privacy constraint, what's the loss in terms of accuracy? So let me show you a summary. So in this problem, here are the mean estimation problem, very simple problem, and linear regression, high dimensional linear regression, generalized linear model, and so on. And the first column here are the standard results without any constraint. So that's conventional statistics. So the first column is known. So D is a dimension, N is a sample size, and S is a sparsity. And here alpha is the smoothness. And the second column consists of two terms. The first term is the same as the first column. So in other words, even without privacy, you have to pay this price in terms of accuracy. What's new is the blue term, the second term. The second term is new. So in other words, because of the privacy constraint, we have to incur a price of the second term. The second term involves delta, involves also epsilon. And sometimes we also have log n, or we also have log of 1 over delta. And the third, so here we have specific method that guarantees privacy and also achieves the performance given here. And the question is, how good is the performance? So we also develop what's called lower bound. Lower bound means that we have results to show, given the data and the privacy constraint, the best, there's no method that can achieve accuracy better than this column. So the comparison that we need to make is the blue column here and the blue column there. If they match exactly, it means that what we have is an optimal procedure, because that's the minimum, the best possible performance that based on the data you have. So if you look at this, you compare the two columns, only the last row we have the most satisfactory result, because those two terms are exactly the same for pairwise comparison. Pairwise comparison means that, think about, say, ranking of tennis players. How do you rank the tennis players? You pick any pair of players, you let them play. And after a few sets, one of them wins. So the outcome is Bernoulli. It's either 0 or 1. It turns out in this case, we have the exact matching rate. So in other words, the method we propose is optimal in terms of rate. And for other problems, there's a difference of log terms. Log of 1 over delta that appears in the upper bound, but not in the lower bound. And we are still trying very hard to close this log gap. But if we ignore the log gap, basically you can see that what we have is near optimal. So in other words, for a range of problems, we have methods and also theoretical analysis that shows those methods are near optimal. And also, we're still working on other problems. Not all the problems are equally easy to solve. Some problems are easy, some problems actually are quite hard. And both in the single server case, in one data set case, and also in the federated setting case. So anyway, in terms of big picture, we have a fair amount of understanding of how to analyze statistical problems under privacy constraints. And what we are interested now is federated learning setting. So we know how to solve a single problem, but now we have multiple data sets, multiple servers. How can we aggregate and incorporate all the information under the distributed privacy constraints and still come up with a good estimate at the end? And the specific problem is less important than the general framework. So as I mentioned, in the conventional setting, we always imagine we have one big data set somewhere to be analyzed. But now there are more and more problems where the data are distributed in different locations. So the question is, how can we aggregate all the informations from different locations to come up with the best possible estimate at the end? So again, this is a repeat of what I showed you before. So you can analyze each data set. You can output a transcript to the center. And then the center aggregates all the transcripts and come up with a final estimate called theta hat. And the question is, given the data and a specific statistical problem, what's the optimal performance? What's the best way to do it? And I'm going to give you an example of nonparametric regression. So it's nonparametric function estimation. If you compare statistics as a field, say with something like math, and you realize that our field is much trendier than math. And for many years, from 1980s to the end of 2000, and this problem occupied a central place in statistics. But by the end of, by the beginning of 2000, people feel that we have almost full understanding of these problems. If you keep track of history, you realize that most of the people who used to work on this problem then move on to work on high-dimensional statistics. So here we have three models. One is nonparametric regression. So you observe a signal plus noise, something of this type. Or it could be an image cropped by noise. It can also be a continuous time model where you observe a stochastic Gaussian process with a drift function f of t. So you can think of this as an analog of nonparametric regression, but you observe continuously. Another related problem is density estimation. So you observe IID, you have IID observations from some distribution, and you want to estimate the density function. So those three models on the surface are very different. But after 2 decades of research, people now understand that those three problems are the same. In the sense that we have many methods. And the students probably have learned many of these methods in graduate classes. And we also have developed very complete theory, like minimax theory, adaptation theory, and so on. In particular, we know that the rate of convergence for estimating the function is of order n to minus 2 alpha over 2 alpha plus 1. Alpha is the smoothness. And you can think of this as Lipschitz or Sobolev class or Besov class. And a lot of papers have been written both for global estimation, meaning that you want to estimate the whole function f, and also for local estimation, meaning that you want to estimate this function f at any given point. And there are also very deep theoretical results called asymptotic equivalence, which shows that for these three models, non-parametric regression, white noise model, and density estimation, once you know how to solve one problem, you should immediately come up with a solution for under each of the other two models. But we are not going to discuss this any further. And instead, we are going to move on to the federated non-parametric regression case. So in this case, we have n servers. We have m servers. So for each I, we have a sample of this type. So originally we only have one sample of size n. We have n IID observations under this model. So you observe this function at n random locations. And in federated setting, you have a total of m machines. Each machine contains n observations. And the f is the same. This function f, regression function, is the same across all the servers. So think of each server as one of us. So I have n observations about this f. You have n observations about this f. Each one of us has n observations. And we could just use our own data to get a good estimate of f. But now we decide to collaborate. We try to learn together while guarantee privacy of our observations. So we have two problems. Under the distributed epsilon delta dp constraint, we want to estimate the whole function f as accurately as possible. Two is we want to estimate f at a point, as a particular point x0, as accurately as possible. And turns out these two problems are different. Estimating the whole function is different from estimating at a point. And the function class we are going to consider is what's called the best of class. And some of you may have learned wavelets in other classes. If you know wavelets, it's easier for you to learn what's called best of space. But if you have never learned the wavelets before, that's okay. It's simply an orthonormal basis. Think about Fourier basis. If you have a smooth function, you expand in the Fourier basis, you get a sequence of coefficients. So a function in the best of space corresponds to a sequence that satisfies this constraint. So it looks complicated, but you don't have to remember anything. Just like a Fourier basis, if the function is smooth, then the coefficient decay. It becomes smaller and smaller. And the only thing that's different is wavelet is organized by resolution levels. That's indicated by this J. And the original observations, remember each server has n IID observations. If you have n IID observations, you can transform the IID observations into wavelet coefficients. Just think about, say, an analog of Fourier basis. Now you have Fourier coefficients. So in other words, observing n IID samples is the same as observing noisy wavelet coefficients. So here's the illustration of that. Wavelet coefficients are organized by resolution levels. And some of you may have experience when the internet is slow and you click on a website with, say, a high resolution image. some of you may have experience and noticing that the image initially is of very low resolution, very rough. Then gradually it becomes clearer and clearer. And if that's the case, it's encoded by wavelengths. And sometimes you go to the same website or different websites, and you see a high resolution image that comes to you linearly. You first see the hair, then the face, then the body. It goes down like that. If that's the case, it's encoded by Fourier basis. And wavelengths actually is very useful. The reason now we can call, say, friends or family members without paying for anything. We have video calls. That's wavelength. So it's organized by resolution levels. And roughly speaking, our method involves 3 steps. The first step is calculate the maximum estimate resolution level, Jmax, and a truncation level, tau. And then on each server, say on the I server, we use the Gaussian mechanism. Remember Gaussian mechanism, we add the Gaussian noise to generate an epsilon delta dp transcript. So we generate transcript on each server, and we can show that this transcript satisfies epsilon delta dp constraint. Then this server outputs the transcript to the center, and the center will receive transcript T1 through Tm. So to give you more details, the maximum resolution level is specified by this quantity. Alpha is the smoothness, and M is the number of servers. N is the number of samples on each server, and epsilon is the privacy constraint. And tau is a constant specified here. And the epsilon delta dp private dp transcript is given here. So we have the sample coefficients. We add the noise with this noise level. So it's very important here that we have this tau here. Tau is the truncation level. It's given in the noise level. And this Jmax is the maximum resolution level. So essentially, what we are doing is originally we have NIID observations, right? From NIID observations, we can transform into noisy wavelength coefficients. So the wavelength coefficients are a very long sequence of vector. Then we truncate at this J level, Jmax level. So we truncate. Anything beyond that, we set to 0. We only keep the beginning number of coefficients, 2 to the Jmax. And for the beginning ones, we add noise to them. And then we output this TJ, the transcript. And because it's Gaussian mechanism, actually it's easy to show that it satisfies the DP requirement. So it guarantees privacy. And then the final estimate is the average of those transcripts. And let me give you some details in terms of theoretical analysis. It can be shown that this procedure achieves this rate of convergence. And again, same as the entries on that big table. It contains 2 terms. The first term, the total number, we have total of m observations, and each m servers, and each server has n observations. So the total number of observations is m times n. And so this first term is the optimal rate if you are allowed to combine all the samples together first. If you are able to combine all the observations together without any privacy constraints, you should be able to achieve this rate. But we also have the second term. The second term involves this epsilon, which depends on the privacy constraint. And so this is the additional cost of privacy. Not only that, it also involves this M. M is the number of servers. And N is the number of observations per server. And let me explain on the next slide. It's very interesting. And first of all, when this epsilon is large, when the privacy constraint is not significant, so you care about privacy but don't care too much. If that's the case, then the cost of privacy is not significant in the sense that the second term is negligible relative to the first term. Statistical error still dominates. But on the other hand, if you ask for a lot of privacy, you want this epsilon to be very small. If epsilon is very small, it's going to cost you a lot. The second term will become dominant. So the error will be mainly driven by the privacy constraint, much less by statistical error. If we look at this rate further, you will see quite a few interesting phenomena. First of all, suppose we fix the total number of observations. Capital N is equal to M times N. That's the total number of observations. So imagine among all of us, we have this capital N number of observations. And suppose we have a choice. We either divide this N observations into, say, small number of people here. And each one of those people will have more observations. So data is concentrated among relatively few number of people or few number of servers. Or it can be spread among all of us. Each one of us have a small number of observations. And this analysis will tell us that this risk will increase with M and decreases with N. So in other words, it's much more accurate if fewer of us have more observations. If we spread them out, say, evenly, and each one of us have very small number of observations, then the end result will not be good. And this phenomenon has an intuitive explanation. It's easier to retain privacy within a larger crowd because each server contains more observations. It's easier to achieve privacy. And another interesting aspect is that the output, because each server output a transcript, right? T1, T2, Tm. It turns out that the outputs from individual servers are not optimal locally. You can easily show that this T1 is not optimal if you only have data on the first server. Meaning that knowing that you have a group of other friends working together with you is very different from trying to solve the problem alone based on your own data. If you try to solve the problem alone based on your own data, you shouldn't use this T1. You should use something else. And also, if n is equal to 1, in the most extreme case, each server contains only one data point. And then it's the least favorable setting. And that result is known. It's called local privacy. And we have similar results for point-wise estimation. If we want to estimate at a point, it turns out the rate is different. And here we have something called nu. It's not alpha. So this nu is alpha minus 1 over p, and which is smaller than alpha. So it's more difficult to estimate in terms of rate. It's more difficult to estimate a point than estimating globally. And also, let me go to the next slide. And there's also very interesting phenomena. Because earlier I mentioned that if epsilon is not too small, then the effect of privacy on accuracy is negligible. The same here for pointwise estimation, but they don't occur at the same place. So in other words, for a certain range of epsilon, it may be negligible for global estimation, but it will cost you significantly for pointwise estimation. So that, in other words, the effect of privacy on pointwise estimation versus on global estimation is different. So the phase transition doesn't occur at the same place. And so in a federated setting, the distribution of data across servers impacts the rate differently, depends on the inferential task at hand. It depends on whether you want to estimate F globally or you want to estimate F at a point. I think I will skip this. There's technically one very important analysis in this type of problem is a lower bound. Whatever method you propose, you try to argue that that's the best possible performance. And for that, you need to show a lower bound, showing that there's a limit to the accuracy that you can achieve given the data and the statistical model. So in the classical setting, we have well-established tools. But under privacy, actually, we don't know. The tools are much fewer, and we still need to develop a lot more general tool for lower bound. But because of time constraints, I'm going to skip this. And what I have discussed so far is a simplest case. We only have one epsilon and one delta. So all the servers are homogeneous. They contain same number of observations. But that can be extended to more general settings. So in the paper, we also consider the case where it's heterogeneous. So Z1 may contain N1 number of observations. And the privacy constraint could be epsilon 1 and delta 1. And for the second server, you have different privacy constraints. Because different people or different organizations have different sensitivities to privacy. Some care much less, and some people care much more. So the question is, can we analyze this in such a heterogeneous way? It turns out we can, but the result is very complicated. There's no simple expression of a rate. The rate is determined by an equation. So I'm not going to discuss that. But if you're interested, you can read the paper. It's on my website. Now, what I have discussed so far is certainly can be viewed as an example, non-parametric regression. You can easily imagine lots of other statistical problems can be formulated exactly under the same framework. You can do this for hypothesis testing. Actually, we are finishing a paper right now on testing. And it's very interesting. Actually, it's even more interesting than estimation, but also quite complicated. You can also think about confidence interval. Suppose each one of us want to construct a confidence interval. How can we collaborate together to construct a confidence interval that's short, guarantees privacy, also guarantees coverage probability? And there can be any other problem. As I mentioned, that it takes much more effort to develop general lower bound techniques that can be used to solve not only a single problem, but a range of problems. And also, we have considered the IID setting. IID setting means that across different servers, the distributions are the same, but it doesn't have to be. And we are also working on a problem we call the Federated transfer learning. So different servers have different distributions, and we want to collaborate together. And there are also other interesting but very complicated problems regarding interactive communication protocols. As I mentioned earlier, the communication protocol I mentioned is the simplest. An analyst go to one site or one server. You analyze the data, you output T1, you're done. But a more general type of protocol is you have feedback. The central server receives T1, T2, all the way to Tm. It has much more information. It can calculate something that's useful to each one of the original server. It can send the message back, tells each server, says the variance actually is equal to 2. And once you know the variance is equal to 2, you may want to update your transcript. Say, I update my transcript T1, now it's T1 prime. So you go back and forth. It turns out for complicated problems, interaction can be useful. But it's very difficult to analyze because of dependence. Because whatever message you receive back from the central server now is a function of all the data, all the transcripts. So it also depends on T1 itself. So you have this dependence. And there are also other type of communication protocols. Right now, what I have discussed is we have a central server, or you can think of having a central government. And now we have Bitcoins. People want to decentralize. It turns out there are problems of this type where you only communicate with your friends. So you don't share the information with only one person at the center who has access to all the transcript. Rather, you only send your T1 to a few other people that you like. You don't send your transcript to the people you don't like. So you have a network of friends. And each node has data. And you can communicate between friends, but not with others. There are some recent work on that by other people. And also, in terms of big picture, what I have discussed, and also the talk I gave 2 weeks ago on transfer learning, these are all examples of multi-source learning. So we have multiple data sources, and we want to aggregate information together in different ways. So in federated learning, we have a common parameter theta of interest to all people. In transfer learning, we have something of direct interest, and we have other data sets that can be used to help us to learn this particular task. So there you have one particular data or one particular distribution of interest to you. And there are also other similar but different problems like distributionally robust learning and meta-learning, multitask learning, and lots of terms of this type. But the key difference between these problems and the classical problems is that in classical setting, it's almost always that we have one data set. And in these problems, we have lots of them. And the question is how to aggregate the information that's contained within each data set. So let me stop here. And I want to show you this picture. I think I've showed many times under different context to show you that achieves good statistical performance sometimes requires trade-off with the privacy constraint. And those two goals are often not compatible you have to lose something or pay a price for something else. And the paper is on my website. Thank you.
So happy to have such a comprehensive and intriguing lecture. So do we have any questions?
Hi, Tony. Thanks for your nice survey. And sorry, I missed your last lecture. One question is in federated learning, people talk about horizontal and vertical federated learning from computer science. Horizontal means we divide the rows, the data, into different clients. But vertical means sometimes the different feature belongs to different client, like a hospital.
Yeah.
Yeah. You have MRI in one, another maybe genomics. And do you think there might be some similar minimax optimal analysis toward the vertical federated learning?
Yeah, I think that's a very good question. Both for transfer learning and for federated learning, that's an interesting setting. But it's a more difficult setting, so let me show you the picture I showed earlier. Here. So whether it's vertical or horizontal, so it can be abstract in such a way. So as long as we have a common parameter theta, and under this model, and under that model, and we want to learn this common theta, I think it should be doable. Unless you don't even have something shared among all the servers. Otherwise, this type of general, at least this type of general setup allows for heterogeneity in the distribution. So you can have omega 1 here, omega 2 there. And the data structure can also vary. But the problem is how to set this up. One is you can do some theoretical analysis. Two is it's feasible in practice. But the short answer to your question is yes, it's possible. But we haven't done it.
Another question may be quite naive. So in many applications, the decision trees and the random forest are widely used in federated learning, especially in finance, like WeBank. Do you think any study toward the analysis on that kind of models rather than the classical Bezos space?
It can be done if you have a good understanding of, say, classification trees. You can run it on each server. And the key takeaway here is that the outputs, the transcript from each server should have low bias, high variance. So bias and variance are not optimally balanced. If you only have one single server, they should be balanced so that the mean square error is minimized. But now you know your friend and the other friend will also output their transcript. So you have more data. Then on each server, you should try to lower the bias. And high variance is okay because you can take an average later. And averaging later will lower the variance, but it cannot reduce the bias.
Okay.
So you will run those trees not too deep. Sorry, you should deeper. You should run the tree deeper.
Reduce the bias.
Reduce the bias and increase the variance, yes.
Okay. So what kind of complexity class might be related to those trees?
That depends on the particular technical tools that you like. There are quite a few recent papers that people have analyzed random forest and also cut classification and regression tree. But for complicated problems, I think people always find a random forest useful. But of course, it's harder to analyze than analyzing a single tree. Yeah, so I would say compared to deep learning, we have much deeper theoretical understanding of random forest. But compared to some other methods like kernel and other methods, it's far less.
Yeah, do we have any other questions?
I have two clarification questions. First is the Gaussian mechanism or introducing noise the optimal way to achieve epsilon delta dp? And the second is there any other criteria for achieving privacy except for dp?
Yeah, as I mentioned, there are at least two that's well known. One is I don't know whether it's earlier or later. One is local DP, local privacy. Here. The distinction between these two notions of privacy actually is quite interesting. It depends on how much trust, say, the owner of data has on the analyst. Suppose I own the hospital, so I have obligations to my patients for their privacy. If I trust you as an analyst, you can come to analyze my data, and I can allow you to see the original data. Although anything that you take away has to guarantee the privacy of my patients. So think about, say, linear regression as an example. So you come to analyze my data, and you take away the regression coefficients. If we want to guarantee privacy, you have to add noise, say Gaussian mechanism or some other mechanism, Laplace mechanism. I'm fine, but at least I allow you to see the original data. And the second case, the local privacy, means that I don't even trust you. You are not allowed to see my patient's private data. So what I do is I add noise to the original data. So what you see is already noisy. And so that even you try to identify the identity of my patient, you couldn't. So that's local privacy. Basically, local privacy guarantees privacy no matter what you do. For regression, I know you only do regression. You're not going to do something else on my data. So I allow you to see the original data. But for local privacy, I don't trust you. And the downside of local privacy is that requirement is too strong. For any of the high-dimensional problem in statistics, high-dimensional linear regression or estimation of large covariance matrices, as soon as the dimension is larger than the sample size, you can show that there's no consistent estimate that guarantees local privacy. So in other words, your privacy requirement is too strong. It's so strong that you couldn't do anything. So people typically don't like local privacy. And also in terms of analysis, local privacy is slightly easier to analyze.
Thank you.
So Tony, in some cases, the parameters are constrained, for example, non-negative or in high setting, let's say if it's a unit norm. So in that case, how do we add noise?
That's not a problem, because once something is private, you add any function, it's private. So in other words, for example, suppose I add noise without, say, positivity constraint. It guarantees privacy, right? Now let's truncate. Anything below 0, truncate at 0. It's still private.
Okay, so let's say if we are talking about the eigenvector, so do we rotate or do we?
That we need to be slightly more careful. Yeah, we do projection or something to make sure that it's still, say, a unit vector or vector of certain, with certain properties. Yeah, it's a valid question. Yeah. For example, say sometimes say you know the vector is a unit vector. So length is 1. Once you add coordinate-wise noise, the length is totally different from 1.
Okay, do we have any other questions? If no, let's thank our speaker again for his wonderful talk.
Okay.